and this term, these all three terms are going to summation block, and I am giving it to go to block. So EV is, we are using directly value of EV, and integration of EV into K2. EV, its integration, and again block to multiply it. EV, its integration and multiplication with K2. The third term, K1 absolute value of EV raised to power lambda signum EV. So EV, its absolute, and absolute raised to power lambda, and this is signum of E1. We have to multiply signum of E1 into absolute of EV raised to power lambda. So the multiplication of both values, after that K1. So you will get our sliding surface. Yes, sir. You can search for sum. Double click on that. Make it plus plus minus minus of whatever you want. So here we are using 3 pluses. You will put 3 plus, apply OK. Is there any doubt? This is power. You can double click and search for power.
As per the equation, double check your equation, see your model, are they matching? In the PDF I shared, double check that. Surface, this side anyone?
Click on 3 dots, after that we will get subsystem, click on it.
No, keep it optional. No. To generate the control input, right? Can you show the equation, control input equation? So now we are, everybody please give attention to this equation. We are now framing this U star, and in that U star, whatever the sliding surface you design is one of the input, right? Apart from that, there are other terms are there. So that U star is equal to B inverse. So B inverse is your INVB in your .m file. It's basically a system parameter dependency. Okay, that is fixed. So B inverse into reference voltage derivative. Okay, V0 star dot means first derivative of the reference voltage, dV0 reference by dt, right? Now second term is zeta 1 zeta 2 plus FL, and all zeta 1 zeta 2 and FL, it is defined here. Okay, that's why this nonlinear control is bit of complex compared to PI control, but we will show you the comparison how fine tuned it is and give the response. So that's why yesterday I told you, you have to sacrifice more computational complexity. You see how many mathematical operators involved here. KPKI only 2, 3, 4 maximum. Here you have signum function, then you have this modulus function, lambda. So many mathematical operators are involved here. To the power e power lambda, that exponent function also here, right? So that makes it is a computationally more complex compared to the PI, but at the cost of fine-tuned response. We'll show that. Okay. So please, all of you, open your PDF, keep it in your side, and we'll show the model how to prepare these equations. Okay. Can you show in the PDF?
So we are using a summation block. We will create all these 4 terms. Let me explain you from basic one. FL is equal to IL upon C0, where IL is our load current. So here is the IL. We are taking it from our converter. This is now FL is equal to IL upon C0. In gain we are giving 1 by C0, and V0 star derivative, V0 reference and its derivative, sigma 2 is equal to alpha 1 signum of sliding surface plus alpha 2 into sliding surface. So S is our sliding surface, sigma 1 into alpha 2 plus alpha 2 into S. This is our sigma 2. For sigma 1, this is our E1. So there are 2 terms. We are adding finally K2 into E1. So this is our K2, and we are taking EV from here. So EV into K2 is this one, and K1 lambda absolute EV raised to power lambda minus 1 into EV dot into signum of E1. So this is a complex equation. You can see absolute of E raised to power lambda minus 1 into EV multiplied by signum of EV. Sorry, search for constant block, type lambda. You can click from .m file. Now simply write -1.
Are you getting? Lambda you already declared in your .m, right?
Yes.
So this makes your first term, right? No.
Sigma 1 first term. I think second term.
Zeta 1. Are you following? Left side, it will give you output. Like K2 is small k. Don't give capital K. It will not find its value. Small k1 into lambda. You can match, I mean, it's a good habit if you can match your equations. Same thing we are just putting. Embedded coding you have to do. But here just like software simulation we are showing. The same total controller, there is a option available in Simulink called S function. S function block. If you are good at embedded coding, you can open that and write this mathematics in that code. So that S function is single block. You can give your input and directly generate U star, or directly generate the pulses even. Because if not good at embedded coding S function, you can use simple MATLAB function. All this mathematical operation we are doing, you can do there. 1 by C naught.
Quadratic for D. and we'll get it an expression for D. You can write it in your notebook. I will tell you. D is equal to D is equal to 1 minus square root of 1 minus 4u, square root of this u is our control input. Before that, D is equal to 1 minus square root of 1 minus 4u, 4 divided by 2. You can search for go to block and give it to u. After that, you will use this u to get our duty ratio, where D is equal to, forget it, D is equal to 1 minus square root of 4u whole divided by 2. So you can derive that equation in simulation.
Pulse generator, I was giving myself a phase difference. Now that phase difference I am giving from the control input. So original plus pulse, then I give the phase shift in that transfer delay, right?
Variable time delay.
Variable time delay. So it is a phase shift is not now fixed. So depending upon how much output voltage you change, it will update that phase shift, and accordingly you get your desired control. Okay. So instead of that phase shift I was giving in the previous example by myself by 30 degree, but now it is through the controller, makes it a closed loop control. Okay. So that is the generate 4 set of pulses. Those pulses will like repeat for other 4 switches following this standard. Okay. Switch 1 and switch 4. PWM22 will go to switch 2 and switch 3. PWM33 will go to switch 5 and switch 8. And PWM44 will go to
6 and 7.
Switch 6 and switch 7. Now this will give to the gate signal of the switches, DAB converter. Time delay. Can you double click that and open that what is to set?
You can just take it as it is.
So it is, you have to select the delay type as transport delay. Okay. The delay type in the top one that has 2 options. Carefully select the transport delay, variable transport delay. You use properly as it is done, and then put the go to blocks and 0. Sliding surface. Yes.
Low 0.75. So why we are using this saturation block here?
No, this saturation is basically you have to maintain a upper band and lower band for the phase shift in order to make the system stable. Between that range you have to vary the phase shift. That's what we are doing. So minus 0.75 corresponds to some degree and 0.25 corresponds to some degree. Between that you vary your phi and control your output voltage.
Or we can say phi value should be in between 0 to pi. Okay.
From the controller. Yes, that diagram we have to follow. Giving all these 4 pulses. Lesson output tracking will do output step change. Sorry? Correct. So now we will do a simple simulation and give you the rest of the thing you can do at your home. We will see the tracking performance. We will give a step change to the reference voltage and see how the measured voltage is tracking. How much overshoot, how much settling time, all we track. So for doing that, we are replacing the V0 reference with a controlled step change. Okay. So that you can find like stair generator. What we are doing, can you open that stair generator? So if you see at 0 time, my voltage is 262. At 0.05 time, I step down from 262 to 209.6. At 0.1, again I step up to 262. Okay, so during those transitions in the reference, how V0 is tracking, we are going to see. Understood? Okay, now we'll run that. So we'll plot the reference voltage and measure voltage one over the other. Okay? Plot. Input voltage we are not touching now, just tracking the output. Yes, so if you see the top color, blue color, is your reference which is fixed at 262. Yellow is slowly going and tracking it. If you remember yesterday I showed you PI controller. It will have some overshoot, then it will come to track. Now here you don't see any overshoot, just carefully see. The yellow color in the top is following the blue color. The second graph is your input voltage which we kept at 6000 volt. And the last one is the
power.
Can you make it fit to zoom? Power, okay. Power, anyway, so you just focus the first one without any overshoot. It is following, but there is a delay time involved. Still you have a scope, whatever the control parameter we choose, you can adjust them so that initial delay time you can manage. Okay. But again, making it too fine tuned, too tight to make it very fast to follow, sometimes system gets unstable. So there where you have to have some theoretical background, what is the range you can select those parameters. Okay. It's not that blindly you put whatever value you can. There is a range you have to follow, and that range has to be derived from some nonlinear theory like Lyapunov stability theorem or something like that. Okay. For what range of those control parameter your system response is stable. Okay. You know the DAV converter power rating we put 500 kilowatt, right? Power is 500 kilowatt, voltage is 262.
Power is a multiplication of output voltage and load current.
Power we calculate output voltage into, because DC power V into I, right? Output voltage into output current, load current. Now you see the yellow is tracking the blue one. And at 0.05, we will have a jump, step down in the reference voltage, and we will see what is happening to power and output voltage. load we are driving from a DAB DC-DC buck converter. It is a buck, right? DC-DC buck means what? Voltage has to be stepped down. And it is called a electrolyzer load fed by a isolated DAB DC-DC buck converter with a nonlinear control. I purposefully showed you the nonlinear because linear is easy. But if you keep this as a reference, when you learn PI control, you can compare with the response. Okay. So let's see what is happening at 0.05 and 1 second. After that simulation, we will close the session.
Sir. Use sample time of 0.1 into TS. In future you want to do with input voltage change. So then you will search for controlled voltage source and you will search again staircase generator. So you can give your input voltage at any interval of time at any value, and set also sample time is equal to 0.1 into TS. Here this one is MUX, so that you can plot both signals in single frame. As you can see here, this is one signal and this is one signal, but here we have two signals coming in single scope. V note actual output voltage, V note reference is our reference output voltage, V in our input voltage, P note is output power, multiplication of output voltage and load current.
Version, so 23 will put, so any other version we can use. Yes. So here we end the session for today and day 3, and tomorrow we will again meet same time, same place. Till then, good night. Thank you.